But this is hearing the broadcast. Well, maybe we can email it later. Okay, we should be on. Okay. Right, beginning, and then I have tab. So, you all have a good morning so far? Good. You're very informative. We've got how many meetings? Probably 3 or 4, right?
Yeah, about 4. I had an hour break. I was kind of take a little walk around.
You can change. Yeah, the most industrial side of campus, unfortunately, but it's close to a lot of things. It's nice being close to the unit. There's a lot that goes on there, and we're just right across the street.
I saw the football stadium.
Oh yeah.
Store.
He says 4 credits, not enough. Which,
All right. Yeah.
he thinks that, yeah, I think it's
Okay, good afternoon. Welcome to Weather Watch. It's certainly a particular warm welcome to our visiting prospective students. I hope you have a great visit today and over the weekend for the length of time that you're here. This is Weather Watch. This is a discussion of the past week's weather, current weather, and future weather. And it's a really informal seminar type presentation that's led by both faculty and grad students. And hopefully at some point in the future, we'll see you guys up here leading part of that discussion. What we're going to talk about today is going to be a cyclone that's just struck the northwestern part of Europe. And we'll talk a little bit about that. The UK, they've had some really strong winds. I want to start with a video. Unfortunately, I think the sound's not going to come out too clearly, but it's really just kind of interesting. First of all, I didn't realize there was a big jet TV where you can just watch planes landing all over the world. I guess it's the Heathrow. And the narration of this is just hilarious. But you can see the planes kind of struggling to land. The narrator is commenting on that. But again, if the volume were hearable, it's like, are you really going to make this? And then he's kind of urging the plane on, go on. But really, I mean, there were some shots earlier when the narrator was looking at the planes came in on approach. They just looked like they're about to land. The winds gusted, and they just took off again and circled sometimes 2 or 3 attempts to land. But again, it's at Heathrow. I think it's at runway 27 out. But let's go to the first tab on this. And what's the nature of this particular storm? Or the second tab, please. And we can bring it up. So here's the storm. This just shows some ice attacks of wind. This is from a forecast earlier in the week, but showing the intensity of this storm. And a record was set for England for their strongest, at least wind gust, surface wind gust of 122 miles per hour on the Needles on the Isle of Wight earlier this morning. So we had a really intense storm. Not much wind, or a lot of wind, but not much rain associated with this. And we're going to look a little bit at the structure of the storm, its development. I did a short WRF simulation, a WRF forecast of the storm based on the 12D data from last night. I want to show a couple of characteristics, then we're going to turn it over to a graduate of our program, Dr. Alex Goldstein, who's in the UK. He'll give us sort of a report of some of the things that he's seen in his perspective on this particular event. So we'll go to the next tab, please, Pete. So this is from Scott Duncan's website, and this just shows, I guess these are wind gusts in kilometers per hour from this website. It's using actually GFS quarter-degree resolution data, and this was from a model run that was initialized earlier this week, and it shows a couple of storms impacting Europe. Here's the first one. That's actually the one that we're looking at, but you can see it as it comes up. It starts to develop well to the southwest of the Azores and then moves into our area. And we'll see it looks like it was the merger of 2 weather events, one that went over us on Valentine's Day on the 14th, and another system that was already lingering in the Atlantic. There was a merger, and then we got this rapid development. But really an interesting series of cyclones. This is called Eunice. I think its predecessor was Duncan, but also provided some really strong winds over the UK. But before I say more about this and we look at the model simulation, maybe we'll turn it over to Alex to say a few words about that. I'll take a moment just to put him in. Hopefully this sound works. And okay, there we see it. Let's see if we can hear you. I can do that here. Hold on a sec. There we go. There we go.
Cool.
Okay,
All right, well,
so, yeah, Alex, take it
yeah.
away.
Thanks, Michael. This is exciting for me because it's the closest I'm ever going to be to being like a CNN foreign correspondent. So, really tough opportunity. So just to correct you, Michael, on one thing, they named this storm that was the predecessor unit Dudley.
Dudley, sorry.
Because they want to make it as characteristically British as they possibly can. So Dudley was the name of the storm.
Dudley.
Yeah, so this was a really interesting storm for me. I go to work every morning. I forecast the energy sector for Europe. And I start my day every morning at about 6 a.m. And so I left my apartment this morning a little bit before that. And it was completely calm with a little bit of mist, which is pretty characteristic of the weather here in the UK. And so for much of the morning, I was answering the same question, which is where is the storm, where is the storm, where is the storm? And I just kept having to tell them it's coming, it's coming, it's coming. And like Michael said, we got almost no rain. In fact, most of the afternoon was spent in the sun, with just consistent gusts near 70 miles an hour. On Heathrow at around 11 a.m. got its first 70 mile an hour gust. Like Michael said, we got to 122 miles per hour. At the Isle of Wight, which is about 2.5 hours south of here in London. And I was actually there this past weekend. Really would have loved to have been there today, being that I love these kinds of events. Some of you in the audience there may know that, especially Zoe, we chased Hurricane Harvey together. So this was the closest I've been to doing something like that. But like Michael said, this was synoptically a really fascinating event. A lot of the weather that we've been getting here across the northern tier of Europe has been driven, in my opinion, I'd love to hear the opinions of anyone there, quite a bit about what's going on in the United States. So we have a confluence of a few things that we can, first of all, we have an extremely strong cold tanks that just doesn't seem to want to quit. Everyone who I work with is asking me when it's going to die, and my response is sometime in the next decade. This thing is just an absolute monster. And so we've seen a really substantial positive MAO pattern, really substantial positive AO pattern. And this has just been recharging the jet over and over again. So the past 2 weeks, maybe even longer, we've just seen repeated cyclogenesis across the North Atlantic, and it just comes across the UK, gets to the North Sea, just batters Germany. So it's been a really active wind pattern. What has made this one particularly interesting is like what we saw in the little Twitter bit there. The initial sort of vortex formed over the central Atlantic. And this is quite different than a lot of the cyclones you've been getting that formed sort of on the northern cyclonic shear side of the jet. And actually, forecasting for the UK has been a real adjustment from coming from the northeast of the United States, where we get these big high altitude troughs that come through. That's where you get a lot of cyclogenesis from. The storms that we get here are sort of more akin to what you'd see on the west coast of the U.S., where you get these cyclones develop on the northern side of the straight jet. But this one developed in the central Atlantic and sort of got absorbed into that really active jet stream across the North Atlantic, and I think sort of crossed the jet actually, and really deepened very quickly to beautiful one-course seclusion. We just got absolutely raked today. The wind was really special. What makes this that much more sort of frustrating, I think, for people in the UK is that nobody ever sees this here. So, they were closing schools today. My boss's 20-month-old son, his school, they were giving 20 minutes notice when they were going to be letting kids out, and so everyone was kind of scrambling. So it was a really interesting day for us here. Yeah, seeing 70 miles plus per hour winds with no rain. Sun was really cool. But again, I'd love to hear anyone else's opinion on this. I think a lot of what's driving this is repeated cold chunks across the United States. The big pattern is really the numbers. So these repeated cold chunks just recharging the jet over and over, keep getting cyclogenesis on the northeast coast of the U.S. It keeps getting up into the Atlantic jet, and it's the way across amplifies. This morning we see operational running 936 millibar surface cyclone near Iceland. These things just keep pivoting around this sort of main node getting to us. And, we're not done with this pattern. anytime soon. Wind farm people are getting a little frustrated because it's just, they can't really sell the wind. But, yeah, it was quite a storm.
So Alex, what's the issue with the wind farms in terms of, I know there's probably limits to how much wind they can take, but what's the issue? What's their frustration?
There's a couple of things here. So, first of all, you're right. There's an upper bound, and they'll actually do something called curtailment, where if you get a certain amount of wind, they will turn off the turbines. So this is actually interesting from an energy pricing perspective, because you start to get into a scenario where there's literally so much power that the producers will actually start to pay consumers to take the energy from them. So there was a thought that this coming weekend we might get enough wind across Germany in particular, where again the producers would start having to pay the retailers to take power off their hands. So it has happened before where retailers were paying, producers were paying up to 70 euros per megawatt hour to take the power. So, if you're a power trader, which is the group that I work for, this is something that we sort of like to see. So, I think the frustration, I'm assuming there was a little bit of frustration from some of these wind producers or some of these power producers, because there's just so much wind, and there has been so much wind for this entire month, and it looks like it's going to continue almost indefinitely. They're just, I don't know that they've had any negative prices, but they're selling their power for 20 to 30 euros per megawatt hour, which is really not very much. So it kind of comes at a fortuitous time, given the fact that there's all this conflict in Russia and Ukraine, and some of the other fuels that are used for power really jumping as a result. But from a renewables perspective, and from a believer in climate change like myself, it's nice to see that we're really cranking up renewables here. So, yeah, we're probably in for this for at least another 2 weeks, in my opinion. Yeah, it's been quite varied.
Any questions for Alex? We're going to get more into the storm in a little bit, but just any questions? And thanks, Alex, for your perspective on it.
Yeah,
Greg?
No, I don't have a question. I wanted to show you the jet stream patterns that I have at some point.
Okay.
Because it confirms what he's saying. This is not going to end anytime soon.
Okay.
It's pretty spectacular.
So we'll get to that. We'll
Okay,
first talk about the small scale
Yeah.
part of it, and then look at the larger scale.
Yeah.
Okay, so we're going to.
Alex.
Yeah, thanks. You'll still be around watching, but we're going to switch, I guess, inputs to storm. So let's stop this and go down to the terminal. First tab on the left, please. And if you do a semicolon L, that should start a loop. And then the first jetpack window on the lower part. Yes, I said jetpack. I'll still use that occasionally. So this is from a war simulation that was started at 12D yesterday, running through 12D, 24 hours through 12D today. And you can see what's plotted here is sea level pressure, sort of near surface winds, 10 meter winds, and beta E at 950 hectopascal. And you can see this really intense, this intensifying storm that gets below 980 hectopascals as it moves over the northern part of the United Kingdom. Beautiful warm sector, but what's really interesting is on the southwest side of the storm, really intense pressure gradient that forms, which is going to be associated in a balanced sense with really strong winds. And this is sometimes referred to by folks as the sting jet, which is often seen on the southwest side of a really intense cyclone. And so that moved into southwestern England earlier this morning. So this run through noon, Alex's time with this cyclone. But again, a really impressive cyclone as it moves into South of Ireland and the UK. If we go back to, just click on that window and just stop it for a moment. Let's go to the next tab, please. And with the loop that we have to go to the next tab up on the terminal. Oh, nice. And we semicolon L. Now, this just shows winds at 10 meters. That's the ice attacks for the winds. You get a nice sense of the structure that localized maximum winds on the southwest side of this cyclone. Of course, I don't have a color bar here, but I think that's 40 knots is the brown that shows up here near the end of this. Again, this is just the model simulation, 30 kilometer resolution. I didn't really have to do anything fancy with this particular run, but just to set it up to give you a sense of the structure of this particular cyclone. Another variable that's of interest to this, and again, if you have comments, you'd like to see something associated with this, please say something. We can click on this to stop this loop and go to the next terminal tab and take a look. Semicolon L that. This will give us, I believe, the potential vorticity in the lower troposphere. And you can see the rapid development of this slug with really high potential vorticity. This is in the layer between 850 hectopascal and 950 hectopascal. So it's lower tropospheric potential vorticity. And this is just really, stop, do a semicolon L again. We can get this further up. Okay. So you can see that it kind of the demise of it as it moves over northern part of the UK. But again, you can see this really intense slug of high potential vorticity in the lower troposphere. This is really just a dramatic development, and then it just moves into the UK. Now, even though it looks like it's falling apart, this is the time when we get those strong winds on the southwest coast of Europe. If we were to stop this around 12Z and do a cross section through that PV structure, I just want to give you a sense of what that looks like. We can click on this to stop it, please, Pete. And go to the next tab. And we can just note the animation on this. We can just click on the jetpack window for that. And then we're going to overlay something on this. So this is a cross section from southwest to northeast through that lower tropospheric PV anomaly, which is this structure right here. We're going to overlay on this the winds normal to this cross section. But this is just a really impressive tropopause fold structure, but just a tropopause wall, which I know is going to be associated with intense winds normal to this cross section. If I had this through the jet perfectly, we'd get a really nice strong wind. But what's really interesting, this local maximum of potential vorticity, which I think, without a doubt, is diabatically generated in this event. Again, I haven't presented the evidence, but seeing structures like this, that low, that high in terms of potential vorticity, it's undoubtedly associated with some diabatic processes. So if we go to that same window, that terminal, type res space norm v, or just norm, and then run that. Hopefully this doesn't work. All right, these are winds in meters per second. In this cross section, again, this wasn't perfectly chosen. I wanted to really go cut through this. Look, associated with this maximum right here, 30 meter per second wind in the lower troposphere on the southwest side of this particular lower tropospheric PV. Really intense jet at low levels. And then this big, deep tropopause type structure that we see here, which I just think is
Question.
incredible.
When you say it's diabatically generated, are you saying the cold air, the radiational cooling at the surface?
No. So what I would suggest here is that it's latent heat release associated with precipitation near the head of this particular cycle.
That would generate low potential vorticity.
It would generate, it's actually a redistribution of low PV aloft and high PV in the lower troposphere, based on the gradient of heating is going to be somewhere, I imagine. And then, again, this is not an ideal cross section to show the diabatic redistribution occurring, but it would be above this region where you'd get the diabatic generation of PV in the lower troposphere, lower PV aloft.
Well, what if that redistribution's done somewhere else, and then this is infected, the residue's infected?
That's right.
Around.
That's quite possible, because you saw that hook that
Yeah.
was coming around, so it may have been along a frontal structure, part of the seclusion that was forming. You had potential vorticity generation along that strip, and then it sort of balled up.
Well, there's a lot of low potential vorticity up in the Arctic near the surface. I mean, very high potential vorticity near the surface. And could this be grabbing into an Arctic air mass and pulling that in at low levels?
Possibly. What I showed earlier with I think it was the third tab that showed the potential vorticity in a pressure level, an isobaric level. Since that's not an isotropic surface, it's not fair to say, is it conserved or not? It's not going to be conserved on isobaric surfaces. But I don't think there's much evidence of it being scooped up from higher latitudes from the south. I think this might be diabatically generated as the cyclones develop.
Yeah, that's what I think too. I think it's on the warm front that's very intense here, and I think it's the production along the warm front, and then the storm relative advection through the warm front to the terminus that piles it up there. That'd be my guess.
So it wraps up. So really nice, fascinating storm to look at.
Yeah, it is.
And we have a data set, so we can set things up if people wanted to look at this in more detail. The last thing I wanted to show, and then we'll turn over to Greg to look at sort of the jet structures, was, I don't have this tab up unfortunately, but if we could do a tropical tidbits. And then we'll go to the Atlantic view for region. For forecast model. Region here. North Atlantic. And then let's change this to Wednesday the 18th. And look at different set of variables. Scroll down, please, a little bit. Oh, sorry, over here. Upper dynamics. And we'll look at 330, which is, I think, and we'll go Wednesday, 0Z. I'll step through this. Okay, first we'll just step, or let it advance a little bit so you can see the evolution of the structure here in the forecast. So there's our cyclone in the GFS, really rapidly heaping as it moves to the northeast. Maybe it had to track a little bit further north than what was observed. But the point is, if we go back several clicks, we can see the origins of some of the pieces that came to the storm. So here's a lot of lower tropospheric potential vorticity. But it appears that there's a merger between something that's left over along this old front, this frontal boundary, which I think, again, this is these purple contours, the lower tropospheric relative vorticity, cyclonic vorticity, purple at 850 hectopascal. The shaded pattern here is the PV associated with the close to tropopause level. And so we see these, and there's a relationship perhaps between this cyclonic PV anomaly, or PV structure here, and the upper trough. But it seems that there's a merger of these two pieces before the real event gets going. So if we step forward, if we go back a few more clicks, in fact, we can trace some of this structure all the way back to things that were over in the Midwest earlier in the week on Monday. But then we can just go forward again and see how all these pieces come together. Front, here come these pieces that begin to interact, seems to me.
Yeah, and they can kind of wrap up in the lower part of the troposphere, but they can't really do it at upper levels. Look at how the PV feature never gets cut off at all. It's just so progressive. Yeah. And you could almost see that in your simulation of theta E. The peak of the warm sector just kept parading across to the east, and it never wrapped up. It was always kind of crushing the potential for an occluded structure in there.
Yeah, so the larger scale environment in which these cyclones develop is going to be dictated by the larger PV structure that can help to form the potential vorticity in the lower troposphere and sort of set the stage for what kind of cyclone you're going to get. But Greg has some ideas about the jet structure that we interested to hear. We'll do the next page.
You can do the 18Z run from yesterday, so we go.
Yep. Whatever one.
Will you close here soon?
No, the 18th, get the 18th. It's yesterday, so it goes through today. Okay, many of you, I've talked to you about the polar night jet, polar vortex, if you will. This, if you remember me talking about this last fall, this was down here. The polar vortex was in the southern hemisphere. This is in the northern hemisphere. I like to look at this map because you can see what's east-west and what's north-south. You look at those polar stereographic maps that sort of are misleading. But if you look at this jet structure, you can see the subtropical jets are the colorful ones, and they're being ingratiated with low potential vorticity, and the color on here is representative of low potential vorticity that's coming from outflow of convective systems in the tropics. You can see these subtropical jets over here. This is interesting, isn't it? What you're seeing is an interaction, a currently, we're working on this, interaction between this polar night jet, which is centered up in the stratosphere. It's actually up about 25 kilometers. The top of this map is 25 kilometers. And this is a three-dimensional surface you're looking through. And when you see something happening like here, where this intersects underneath, you're looking at the subtropical jet entering the polar night jet. It's up very high. And as a subtropical jet approaches it, the polar night jet deepens down, the subtropical jet deepens upward, and they meet to be a continuous jet stream all the way up, not at the highest values, but a continuous strong wind. When they meet, that changes the dynamics, the quasi-geostrophic circulation. And you can see they've come together here over Europe. And I think this is key to why everything is happening. I think when they come together, they create quasi-geostrophic circulations that draw air into the system. It's creating these winds. So rather than the winds at the surface being entirely baroclinic, driven by cold air surging from the north, they're driven a lot by air from this jet interacting here and then accelerating a lot, creating a vacuum up high, which is pulling air up and air in. And we've seen this happen a number of times before. Nothing like this year. This year is quite interesting how many times these interactions are occurring in so many places. It's interesting to watch the subtropical jet here come along. It's not arching to the north like it might typically do, but instead, a piece of it is peeling off and coming into this jet. Animate through this.
You want to step or? You want to step or just let it go?
Just let it go. I want you to get it. I want to show you basically what's happening. As you see this subtropical jet come across, it's kind of splitting, and a piece is coming up and interacting with this jet as if it's drawn in. Another piece is overturning like a Rossby wave, a breaking Rossby wave, and as it overturns, you see it forms another westerly jet along the equator. This is characteristic of breaking Rossby waves. But you see this go up, enter the jet, accelerate, and then come back again. This one goes up, same thing, and it's happening over here, over Europe. But in the next week, this is a 1 week long sequence. Over the next week, you see multiple interactions coming across here, one pulse after another entering Europe. And the formation of this low latitude subtropical jet down here, which is not necessarily interacting with this polar night jet. One thing that seems to be absent from here is very many polar jets, which are, in my opinion, polar jets are old subtropical jets that move around the middle latitudes and survive off of baroclinicity. But we're not seeing much of that this year. Mostly we just see the subtropical jets and the polar night jet up high. These subtropical jets are splintering off and sending pulses into the polar night jet. Early in the season, we did not have a polar night jet as early as it normally would occur. And so something is a little strange this season. We finally got a polar night jet, and once we got it, the general circulation is dominated by these pulses of energy, potential energy, that are pulsing from the tropical area. This tropical area with these subtropical jets is where the tropical tropopause is high. And we're seeing tropical plumes coming up and interacting one after another with the polar night jet. And this seems to be defining our weather. So what we're doing now is we're trying to make a movie of this for a 1 year movie, so we can watch how this has evolved since last year, and I'll bring that in later on this semester. Megan Schaff and I are working on this to try to get an animation of this. But I think when you look at this in kind of a three-dimensional perspective, looking down the atmosphere from above, you can see these interactions as being very important. And you see these pulses of energy being very important. These pulses of energy that are interacting with the polar night jet. We lost it, Pete. Oh, there it goes. These pulses of energy are indicative of Elias and Palm fluxes of energy, potential energy, toward the pole. And the Hadley circulation is really sending pulses of energy toward this polar night jet, making the connection. And this is how energy is being exchanged in the general circulation. You see, in the southern hemisphere, that kind of exchange is not occurring right now because it's their summertime, and they're getting various small jet streams here from periodicity, but nothing exchanging energy with a polar night jet as it was earlier in the year. So anyway, I thought this is interesting to look at right now. From Alex's viewpoint, I think these kind of interactions are very important. Whenever we see these jets interacting with the jet above, we get tremendous storms at the surface because of the divergence aloft, I believe, and the acceleration this produces. And this produces very strong winds that seem to have no apparent baroclinic instability associated with them.
Got a question in the back?
Yeah.
Well, I see, if I have an individual test stream in the polar night jet, it has to have the positive circulation to accelerate downstream. Now, if I think about the thermodynamic equation, I can scale vertical motion in the column based on stratification. I know it's highly stratified. At the same time, it takes very little vertical motion to achieve the temperature because of stratification. The convective term in that equation. So, and it's the air's thin, no mass. So I guess I don't see how circulation at 20 hectopascals is applying that amount of mass to the surface where it's more massive.
Well, the circulation is sort of a effect as opposed to a cause. The momentum associated with these jets is not really what's driving this. What's driving it is the potential energy that's contained in these anomalies that are moving poleward from the tropics. The tropics put high potential energy, very cold air, up in the upper troposphere, lower stratosphere. And then that cold air, as it moves poleward, and it moves poleward almost like a density current, it looks like. It's probably gravity wave-like. As it moves poleward, it interacts with the thermal effects of the ozone hole, or not ozone hole, but ozone minimum at the pole, causing a polar jet, the polar night jet. And as they interact, they create a deep baroclinicity. And I think they also, once they interact, they create quasi-geostrophic circulations that corral the baroclinic energy that's at low levels from the more diffuse temperature gradients. They pull them together. And so they're kind of a catalyst that creates this relationship. I don't know if that makes any sense.
Great, no good. Hey, John's gonna get ready to start. Yes,
I was just wondering if you still have the cross section up.
yeah.
Having looked at a fair amount of these, I'm wondering at what point, if you had to draw a contour on there that depicted stratosphere ozone or radiation, to actually truly differentiate between stratospheric air and tropospheric air, where would you draw that relative to, say, the 1-2 isotope?
Well, I think this is speculation without having done any deep analysis. But I think most of this potential vorticity you see here is all stratospheric. This air has origins in the stratosphere. Right. I think all the way down to 700 millibars here. Yeah.
No doubt.
Turn over to John for the current weather.
Thank you, Michael, and thank you, Greg. I had one question for Alex I should have asked. I wonder if Prime Minister Johnson blends in a little bit more this afternoon in London, given his conspicuous inability to locate or use a comb. You know, if the wind is blowing 70 or 80 miles per hour, maybe everybody looks like Boris. I don't know. Here's our surface map. Maybe Alex wouldn't be in a position to answer that, but nonetheless, it's a question of interest. Chilly day today, and yesterday was chilly and windy. I mean, I'm walking around campus a little bit in the afternoon and then in the evening. boy, it really kind of bit at your ears last night. Not unusually chilly, so Greg was right last week. It wasn't, what did we call it? Brutal cold or something. It wasn't brutally cold, but it was cold.
Incredible, was it?
I can't remember what I
I can't
said.
remember now.
I can't remember. But I can tell you this, I don't have the diagram. We've slipped to 18th warmest of the Northern Hemisphere at 850 this winter. So it's been a really weird winter in so many of these ways. It's been fairly stormy in certain places, but it really hasn't been systematically cold around the hemisphere. But here's our picture for today. Some snow in the Lakes region in the eastern part of the United States. It was 53 this morning in Boston. It's 42 now. So finally, it's chilled off a little bit. But it's still, look at it, it's still 52 at Martha's Vineyard. So it's still really warm. And this is immediately post-frontal. As this feature has gone across the continent, you'll see that in the satellite in just a minute.
Hey, John, look at North
Yeah.
Carolina, across eastern North Carolina, where the front is.
66 at Hatteras.
And then 75.
75.
And then look just to the northwest.
Yeah, and then it's 57, 54, it's 39 at Asheville. Maybe that's Hickory, I don't know if it's Asheville, but it's really chilly, yeah, and brutal. Tremendous temperature contrast associated with the cold front that's now largely offshore of the eastern United States. And you'll see in the satellite, there's not that much structure to the cloud mass associated with it. So it's kind of, but it's not that it's not precipitating, it's just that it isn't really well structured. It's really intense periodicity. So I'm eager to see what it looks like at 850 in a minute. Well, wait a minute. We got to stay up in this region because this is going to be the main weather story for this afternoon. I want to give Philly a brief part of the discussion. We have heavy snow in parts of central Minnesota. Benji with Benji.
Alexandria.
Alexandria. And, this is south of Grand Forks. I'm right about that, right?
Fargo, yeah.
Fargo, okay. And then moderate snow in,
Bemidji.
oh, what, that was a question mark. Flo. I'm not sure you know. But I know I don't, so thanks, Benji. So a pocket of really intense snow here in the sort of northwest portion of the state of Minnesota, crossing the border into North Dakota. That's part of a system that we'll see, I think, it's too bad we couldn't quickly draw an isobot on it, but the system is kind of organized right around the lowest pressure is
Further to the north.
998 or something like that. Yeah, okay, so it's right there in International Falls. I know that. So the cyclone center is about here. It's a beautiful looking clipper, but it's not a weak one. And it's got some potent snowfall in the sort of southwest quadrant of it. So that may visit us later this afternoon, which will make our day quite interesting. So I'm excited about that.
Perfect weather for the 20th anniversary.
Yeah, and it's been 2 years since we had a 5-inch snowfall here in town. I thought it was longer than that. It's only been 2 years. The last time was February 9th, 2020. So it's not really that spectacular of a record, but it's something. I'm scrounging for awards for this winter. They're going to be few and far between. Let's avoid going across the country, Pete. I want to take a look at the satellite movie and then the radar and then a couple of the upper.
We have an update also from Alex online about the Prime Minister.
Oh.
His hair apparently is currently in Germany.
Oh. That's excellent. Very good.
So let's see what
He looks
happens.
like the abominable snowman in Rudolph the Red-Nosed Reindeer. I mean, it's the same
Yeah.
hairstyle. It's remarkable.
Visible.
Infrared, please. Oh, okay.
Yeah, sorry.
So that's all right. Here's the big cloud head associated with a storm that's up over the Maritimes. But notice how ragged this cloudiness to the south and west looks. But that is associated with the frontal structure that's really intense. I mean, in terms of its temperature contrast. My eye, though, was drawn immediately this morning to this beast. This is a really nice looking cyclone. And there it is, right north of the border, a little bit to the east of International Falls at the current time. And this cloud map, cold clouds at the top, we don't really know yet until we look at the radar what it looks like underneath. But you can see a beautiful comma shape with hints of a frontal structure in the warm frontal part, and then clearly the cold frontal part, and the air is chilly back behind it. So it's a really nice Clipper-looking system, although it looks better than a Clipper, actually. I don't know if that's starting. See when we take a look. And one can get the impression of a big ridge over the west coast, even in the infrared satellite image, we'll see that. That's 500 millivolts in just a minute. But the tendrils of this stream of air come all the way from the eastern Pacific subtropics into that cycle. So that's kind
So
of
John, it's unfortunate that we're in the warm sector, but it doesn't feel like we're in a warm sector.
yeah, that's right. That's right. But we definitely are. We're right in that warm sector, and but it was 8 degrees this morning at Madison, -1 at International Falls, 3 at Green Bay. The only chilly part of the country really today was here. So okay, so here, look at big and small. So they come in all shapes and sizes. Let's take a look at the radar first, Pete, just to see where it's precipitating. in that whole complex. This morning, it looked a little more ragged for this storm than it does now. This looks like it's becoming a little bit more organized on a line from, say, Houghton down to far southwestern Minnesota. And, but you can almost pick out a cold frontal and a warm frontal portion of the cloudy, the precipitation in the echo. And it's widespread. So I guess if it snows here this afternoon, it might look interesting for a while. I think that's what they're even talking about, squalls, right?
Yeah.
But it won't really probably turn out to be very much, which is almost the perfect situation by the time we get to February 18th. And you heard me say it.
Yes, he said it.
You know, I mean, if it's, I want it to look wintry, but I don't necessarily want the residue anymore. It's too late in the season. Let's move on. So,
Let's record that. And,
yeah.
It's on the live stream.
Cut, print, check the gate. Moving on. Here's the cold frontal precipitation off the coast of the east coast of North America. It's speckled with convection, of course, like at southern latitudes, but not really very well organized, as was indicated perhaps by the satellite image. And then lake effect snows off of Lakes Erie and Ontario, parts of New York State, Pennsylvania. And that's about it for the, you know, where it's precipitating around the country today. I want to take a look at the upper level charts to see what the structure of this thing is, and then if we could, we'll go to my QG Omega pictures, because it's kind of interesting what that looks like today in that region. So let's start at 500 millibars, please. So this is 12D this morning. Really nice looking setup. So strong baroclinic northwesterly flow here. It's you know, minus 30, minus 40 in this isotherm right here. That's minus 45. Sorry, this is minus 40, and then that's minus 25. So a really intense baroclinic zone across the western prairie provinces in the Yukon of Canada. Northwesterly flow. It's hard to determine whether there's geostrophic cold advection or not along this. It's weak, I suppose. There's a very nice, though, curvature feature right in southern Manitoba and northwestern Minnesota. And that's almost certainly tied to the development of this cyclone that at this time, earlier in the day, was over here. It's kind of right at the exit of that feature in the region of strongest curvature. So we'll keep that in mind when we go and look at the vertical motions, the QG vertical motions, and we can split them up into a couple of different portions and see what they look like. The baroclinicity that was evident at the ground and was fairly intense is also intense at 500 millibars. This is a 10-degree corridor of temperature contrast from northern New England all the way down to central Kentucky. It's well to the west of where the surface front is, but at the time I think it was along the coast. But that just indicates the backward tilt of the structure and the fact that it's a fairly deep cold frontal structure for sure. And even one gets the sense that there's baroclinic structure on the northwest side of that cloud head at 500 millibars, down shear of a region of curvature at the southern end of that deep upper trough. Look at these heights over the archipelago, 4730. You know, you've got to climb 4.5 kilometers to find 500 millibars. That's really cold. I don't know how many times, I don't see an off, but I see an analysis of minus 52.5 at 500 millibars. I don't know if I've ever seen an observation that cold, but that analysis gets close. So pretty desperately cold. And we're at the end of February, it's almost at the end of February. So this is sort of a relentless, persistent chill over the eastern part of North America. Let's see what it looks like at 700 millibars. And at 700, you know, it's just what I expected. The orientation of the isentrope drastically changes relative to the isohypsis. So the geostrophic temperature advection is strong and cold over southern Saskatchewan. And you can see that's kind of feeding into the location of the cyclone center, which at 12D at 700 was over the southern part of Lake Winnipeg. And there's a bit of a thermal ridge right there at the curvature maxima, so it's a really nice structure, even as high as 700 millibars. And then 850 would be good. Yeah, look at that. Beautiful cold frontal structure, unusually nicely pronounced for this type of storm in this location. And then the warm front is even nicely pronounced as well. Maybe if you had a little more imagination than the computer, you might draw a fairly intense baroclinic zone here of 15 degrees instead of somewhat scattered over the lake. I would have done that. But it's a pretty nice looking cyclone at 850, relatively low height. And look at the baroclinicity associated with this thing along the east coast. That's 5, 10, 15, 20 degrees across this strip. And even more intense over northern Maine and southern maritime Canada. So very impressive. But this is a really nice looking storm. I'm quite excited about that. We haven't looked at the jet level, so let's do that, Pete. Let's go to 300 millibars. Keeping in mind Is this 400 or 53? That's 3. Keeping in mind where the cyclone was at 12 feet is located right about in this portion of northwest Minnesota, northeast North Dakota. So it's in a nice position, down shear of a very intense jet at 300 millibars. There's an exit region circulation that may have something to say about mass evacuation there. Also, some positive curvature. It's all kind of nicely put together just south of Lake Winnipeg. And stands to be continually energized as the day goes on, given that structure. And then on the eastern seaboard, probably an amalgamation of the polar and a subtropical jet. I'm guessing this part probably will disappear a little bit at 200 millibars. This part will be amplified. We'll see if that's true. But this is an energetic system. And we saw the low-level variability is intense, so it's not surprising to see a strong jet there. It is interesting sometimes, though, to see what types of jets are up there. So can we go to 200, Pete, before we leave the jet level? Yeah, it's kind of a mixed bag. I think it's, I didn't pay attention to the numbers. I guess I should have. The jet looks largely the same, perhaps a little bit weaker at 200 millibars along the southern states, and maybe a little stronger in the northern part of it, 163, 163. Can we go back just so we can check the number? I should have done it before. Sorry to waste your time. 175, it gets weaker, and this one was over 170, I think, too. So the whole thing gets weaker. Maybe it's not two separate jets, but that's a little bit esoteric. The important thing is I want to now, for the last part of the discussion, is just go and take a look at some of the vertical motion forcing that are going on in that region where the cyclone was developing this morning, and then go ahead a minute or an hour or two into the future. So, yeah, thanks. So, what happened?
I assume it's weird on this thing.
Let's go to 12 will be 12D. So that gives a little bit of time to, this is from the 0 hour forecast. So valid at 12D. This is 700 millibar QG omega. Where it's yellow, it's ascending, and it's every effectively microbar per second. I think it's decipascal per second. And then the blue is subsidence. And the dotted lines are 500 and 900 thickness. It gives you an idea of something about the thermal structure. And in that thermal structure, you can see a little bit of a wave right there in the Dakotas, right along the Mississippi, the Dakotas and Minnesota. And that's coincident with ascent to the east and descent to the west. So that's a potent region of ascent, not equaled anywhere on this large domain, including off the east coast of maritime Canada and the Gulf of Alaska. That's the strongest 700 millibar updraft, and it's coupled with the strongest 700 millibar downdraft. So this couplet is quite intense. That's probably not surprising, but it's nice to see that. Let us take a look, Pete, at a partition of this now and do a couple of different pieces. First, the part that is associated with a long isotrope convective divergence. This is usually the largest part of the total omega. It's only one level, I know that, but even so, one sees a fairly impressive couplet forced by Q vectors that are converging or diverging along these dashed lines, not across. So this is the what I call the shear-wise part of the vertical motion forcing. And that's always kind of aligned in couplets along the shear, and the shear is parallel to the picture. Let's see what the transverse part, the part that crosses the shear line, looks like. Oh, very nice. Look at this. So here's the warm frontal ascent, and here's some cold frontal descent, perhaps. So there is this tendency for couplets to align across the shear as well, and they are more often associated with frontogenetic activity. Really interesting. I've not seen this before.
Sure.
And then here on the East Coast, you see the same thing, ascending in the warm and descending in the cold.
Yeah, I suspect, given what you've said earlier, with the structure of the system that it's developing, at a later time, we'll probably see more of a cold frontal.
I think we will too, yeah. This is 12D, so I have a feeling for this afternoon it's going to look more interesting. However, unfortunately, this part of the vertical motion from the QG system, the vertical motion associated with frontogenesis, is always underplayed because the system of equations doesn't really, deal with them in an adequate fashion. Hence, sort of in elitism. Let's go 6 hours later. So this will be more valid now, Pete. Let's see what it looks like right here. Yeah, that's a strong couplet still, and it's moved right over to the right of the arrowhead. And that looks largely the same with skies filling with clouds near us as a consequence of some of the beginnings of the upward vertical motion. Let's do the same split. So first 18 hour there, and that distinction is maintained. That's stronger. So is the descent. Let's see what if the frontal part of it shows up a little bit more vigorously at this time. No, actually, no. It has, the cold frontal part does. Here's the subsidence and the ascent. This is the warm frontal ascent, so something funny's going on here. It's partly an amalgamation of these two systems just to our south and west. Let's do another partition at this time, Pete, which is, first, I'll show you this. This is the cycle of Trenberth Omega. This is PVA by the thermal wind. It's really pretty good. I mean, this is now 75 years old, and it still tells you something really interesting about weather systems. But this is all vorticity affection just by the thermal wind. That's the whole, all the forces. But we can split that up into the shear and curvature vorticity pushed around by the thermal wind and see what that looks like. So let's take a look at the shear vorticity affection by the thermal wind. Very small. It's a small part of that. Right? And then the curvature part. But notice, can we go back? Sorry, Pete, I should have said this. Remember, we had a strong northwesterly jet. The shear is going to be right here, maximized right here. The thermal wind's crossing it, so you have aspect. What about the curvature? It's bound, as we already know, to be the larger piece. And yeah, it's really a major part of the story here for the ascent this afternoon. And one more time, we'll just look at the total at at 24 hours. This will be 0Z. This will be about 6 o'clock tonight. And there's Madison. So whatever's come, the maximum vertical motion has moved a little bit past us. We're right about at the 0 line by 6 p.m. So I suspect we see whatever we see between 2 and 4, or maybe something like that, maybe 3 and 5. So that's all I have.
Okay, let's just do one. I know people are about to go to lunch. Next, right here, be fine. Run, and we'll go down to the bottom. And I have to start with John's favorite meteorogram.
That's meteorogram.
Meteorogram. Okay. And so, temperature, dew point, and here's precipitation. And here's this period. So this model was 7 and 5 initialized, control Z this morning, runs out 60 hours to 0Z Monday, so Sunday evening. It actually is bringing in the precipitation in a little bit later than I would have expected after 0Z, after 6 p.m. But you can see with the arrival of the precipitation, we begin to see this big drop in temperature. The sun's also setting at that time. Cold weekend coming up. Tomorrow's going to be pretty cold. Maybe not brutally cold, but uncomfortably cold. And then we're going to begin to warm up when we get into Sunday. So Sunday's a big warm up. So one of the characteristic differences between a few weeks ago and now I think this week is we're seeing more variability in the weather at our latitude. We're getting weather systems coming through every 2 days as opposed to being kind of stagnantly cold for extended periods of time. Let's look at the time height section just to get a quick sense of what's about to occur. In yellow is our isotropes. Green is the 1.5 Gunch vorticity surface used as a proxy for the dynamical tropopause. We have ascent in blues and minus omega here, and then the relative humidity in red. And so time runs from left to right. And we see the arrival of, before the upper trough arrives over us, we begin to see significant ascent occurring right around 0Z. You can look really closely at the wind field, the strong southwesterly winds, things warming up significantly just before the arrival of that front. So during the course of today, it's going to be warming up, feeling much milder, but wind chills are going to still be low because of the strong winds. Clouding up by mid-afternoon, and then we get that shift, and that's around this time period when we're expecting to get some of the precipitation. The descent comes in right after the passage of the upper trough. Strong northwesterly winds, and then tomorrow afternoon the winds begin to die out, but also shift to the southwest, and that's when our big warm-up occurs once again, with some more clouds occurring later on Sunday afternoon.
How much precipitation were you predicting?
This was on, let's go back to the
half an inch of snow. 0.5, 0.05.
Snow. Half an inch of snow.
it'll likely be frozen precipitation. We're looking at 0.05 or so. So not a lot with this. I think the Weather Service is going maybe in terms of snow, it's 2 of 10 to 1 ounce, half an inch of snow. We're about 0.2 to half an inch for our area. When's that going to come through? If we go back a quick, please, Pete. And rather than looking at the full map, let's go down to 6-hour forecast. 12 Z's, that would have been just around noon. This is the cumulative precipitation ending in the last 3 hours. At that time, here are the brisk southwest winds. The front hasn't yet made it into Minneapolis, but still southwesterly winds. And again, most of the precipitation well to our north. You can see nice circulation. Let's go ahead to the next map time, 3 hours later. Still not quite here, but again, this broad, strong southwesterly flow You can see the surge in temperatures here with the isotherms, nice thermal ridge, and the wind shift. It's still not quite here by 9 hours of forecast, so this is 3 in the afternoon. We go ahead, one more 12-hour period, 6 p.m. Just beginning to arrive here. And again, you see this nose of really warm air just ahead of the front.
Yeah.
Nice confluence along this, which I think some of this precipitation perhaps is going to be associated with the front, in addition to the arrival of the upper trough.
Yeah.
We've influenced those two aspects, bringing high circulation here with precipitation. And presumably will be moist enough for us to get at least some freezing. If we go ahead to midnight tonight, you see that's when the temperatures really have tumbled with the 18 hours in the forecast. Well, that front is well to our south, and we're now in the really cold air, and again, truly uncomfortably cold. The temperatures are expected to drop. These are in degrees Celsius, so not that bad. It's minus 16.
Where does uncomfortably sit on the brutally scale?
We'll color code these by rough comfort next week. But there's the front, the precipitation's over, as John was saying, pretty quickly after 0Z, it should be over. Let's take a quick look at, and then we'll go to the next tab. I'm not going to spend too much time on the forecast this weekend. We're going to warm up. But if we look at, we can just look at the 12 hours of the forecast. This is for the GFS. GFS also actually seems to have this just arriving in our area. We can actually zoom in.
It's a very intense little precip max along
Right.
that front. And it's an intense front, so it's really nice.
Yeah. So here we are, just to the northwest. So again, the MM5 is running at 90-kilometer resolution. It's pretty coarse, but still has the, this is consistent at least with the arrival time here with the GFS of the snow just around 0Z, so just before 6 p.m. Go ahead, just 3 hours of this. See that comes through nicely. So it's really a nice frontal pass with that. We could compare with one last thing. Let's go to the MAM. Go back 12 hours. I think all the models are having actually a little bit of liquid precipitation just ahead of it with a warm nose ahead of the front. But this has the precip already through us by 0Z. So I guess anytime between 4 and 7 this evening, we're going to expect to get precipitation, maybe before 6:30 if you want to sharpen it up a little bit. We'll be getting some snow. And a abrupt shift in the wind direction and things temperatures beginning to plummet. If we go ahead to Sunday afternoon, so let's go to 60 hours of the forecast. Late Sunday. And our thicknesses have recovered above by 40. If you look at surface temperatures, we're going to be pretty decent. In the 34, and presumably if you just went back 3 hours of beach weather.
Put some holes in the night and put swimming.
39. So, nice weekend coming up. Again, I know it's running late, folks have things to do. But this upcoming week, next week, looks like we have a couple shots at some periods of snow, but nothing significant, he says now, and then next week we'll talk about how much we actually got. But, a few chances of some snow earlier next week, but nothing feels like a blockbuster event. Most of it maybe more north than maybe things precipitation. Anyway, well, thank you. Alex is still on. Thanks, Greg. Thanks, John. Thanks, Pete, for running this, and thanks for the questions from the audience and your participation. Have a wonderful weekend, and see you next week.
Thanks, Michael.